Hey everybody, welcome back to AIT 1002 Power Development. We have talked so far about our sources of electricity. We've talked about heat being a source of electricity, light, pressure, magnetism, things like that. So we've talked a little bit about sources, okay, and then we talked about how in our alternators lessons, how we develop three-phase power that's used in industry. We talked about how the power plants develop this three-phase power, how we run it across our transmission lines and into our factories and into our facilities. And then we take that three-phase power, and in our next lesson that we had, we take that three-phase power and we run three-phase motors. That's the heart and soul of industry, whether it's hydraulics or compressed air or direct drive or anything, it's run with a three-phase motor, okay? So we've talked about where the power comes from and how we're using it with a three-phase motor, but we've not really dealt much with DC power. Now we talked a little bit about DC power in the alternators lesson. Remember, we had to vary the DC voltage going into the alternator, and that varied the amount of power coming out of the alternator. So we haven't touched a lot about that, touched on that very much at all, but we are going to in this lesson, okay? And if you remember, this is the symbol for DC. It's solid, it's straight, okay? Whereas AC sine wave, the AC symbol was up and down, okay? It's fluctuating, it's oscillating, okay? Whereas the DC is a solid source of power, okay? It's got its advantages, and we're going to go over those as well. Now, when we talk about DC power, probably the first thing that comes to mind, as we talked in lesson 1, was the dry cell and the wet cell battery as well, okay? So, and we can also create DC power with a DC generator, okay? Now, those are not real practical applications for DC, to get DC power, okay? Most of our DC power that we use comes from what we call a power supply, okay? This is one example of a power supply. We use this in the PLC class. This PLC, the PLC requires some DC power for some input and output devices, so we get it out of a power supply. Another power supply here is a little heavier duty. We use this for testing a lot of things. We can vary the voltage going in and it will vary the voltage coming out, but this is a much heavier duty AC/DC power supply. So they come in all shapes and forms. And like I said, if you remember going in our lesson, our second lesson, we needed this DC power to supply power for our electronic devices, our computers, our laptops, our phones, and things like that, and also for our automotive purposes as well. But we also use DC power in the power production plants, okay? So if you're on back up here and just talk about this for a second and review it a little bit. Remember, we have the spinning rotor of that alternator, okay? And that rotor spins inside the stator. You should remember all this from our alternator lesson, okay? And it spins inside that stator, okay? And basically what's going on is we have a spinning magnet, and that magnetic field induces a voltage into the stator windings, and that stator windings is connected to the leads that connect to our three-phase motors and things like that downstream, okay? But remember, we put DC voltage on the rotor, the spinning rotor. We did this through carbon brushes, okay? And we transferred that DC voltage through the carbon brushes and into the spinning rotor. Remember, if we increased the amount of DC voltage on the rotor, it created a stronger magnetic field, a stronger spinning magnetic field. And that stronger spinning magnetic field resulted in a stronger voltage, a higher voltage coming out of the stator to provide us more power on our power grid, okay? So as the demand for power at the power plants increases, they in turn, it's not quite as simple as this, but they in turn increase the voltage going into that spinning rotor, and that creates a stronger magnetic field to help keep up with power demand, okay? So, but we are actually using DC power in the power plant production, okay? But the way we do this is through a series of what's called rectifiers, okay? Now, rectifiers come in all kinds of shapes. They're solid state devices, and basically what they do is they take AC voltage, that's varying AC voltage, okay? And then they output a solid DC, or close to a solid DC. Like I said, they come in all shapes and sizes. There's this right here. We've got one here in the lab that looks a lot like this, where we connect our AC voltage and we get DC voltage out. We're going to cover that here a little bit later. But this is the symbol, or this will be a schematic that you would probably run across for a power supply using a rectifier, okay? So I want to go over all of this for you too as well, okay? First of all, we want to talk about this symbol right here. This symbol right here is a transformer. Now you should have already had some background with transformers from some of the other previous classes. You should have learned quite a bit about those. But remember, this is a transformer, and a transformer simply takes a higher voltage coming in, a higher AC voltage, never a DC voltage, but a higher AC voltage, and it steps it down to a lower AC voltage. Now, you do have some transformers that will step them up in some cases. In the industry, though, as you're going to be a technician on some manufacturing floors or some type of industry, you're probably not going to use a lot of step-up transformers, maybe in furnaces and things like that. The light furnaces off under pressure, but for the most part, your transformers are going to be stepping voltage down. So we put a higher voltage into our transformer, and we step it down on the secondary side. Again, the primary coil is where we put our voltage going in. For example, I'm just going to use a round number, 120 volts, household current, okay? Put 120 volts into the primary coil of our transformer. It steps it down to a lower voltage. And in this case, I'll just use 24 volts AC, okay? So we've got 120 volts AC coming in to the primary coil. That's our higher voltage going in. And then we, as a result, we get at these 2 points right here on the secondary coil, we get the lower 24 volts AC. And again, you can vary the input voltage and it will vary the output voltage, and that's a whole nother lesson. But for just kind of rehashing a little bit what you should have already had in your basic AC/DC class. But you got a higher voltage coming in and a lower voltage coming out. Keep in mind there's still AC coming out of the transformer. Okay, so this is our rectifier right here, and I'm going to break all this down later, but the AC voltage comes into our points right here on the rectifier, okay, and as a result, these two nodes right here will give us DC power, okay, so whatever our load device is that we're trying to power, whether this is a resistor or whether it's a light or anything else that's run off of DC, this is where the DC power comes from. So we take it, the voltage, we can step it down, and then we can rectify it, go into AC, rectify it, and come out DC, okay? That's the very simple, that's the 10,000 foot view of how the rectifier works, okay? But again, remember your symbol, your coils, and your primary, secondary, and this is a rectifier that gives us DC voltage to power our load or device, whatever it is we're trying to power, okay? All right, so again, as I said, this is where the positive DC comes out and the negative DC as well. You got to have both of those, just like a positive and a hot and a neutral with AC. You got your positive and your negative with the DC. Okay. Now we got two types of rectifiers. We've got known as a half wave rectifier and a full wave rectifier. To be honest with you, I'm really not going to go into half-wave rectifiers because we don't really use them that much, but they are in existence for some electronic devices, okay? But for what we're going to be using as a technician out on an industrial floor, you're going to be using full-wave rectifiers a whole lot. In fact, if you go into my motor controls class, we're going to talk a lot about rectifiers and how they work in variable frequency drives. So this lesson that we're talking about now is going to apply in a couple of classes later down the road. So you're not going to hear it and then forget about it. So it's a full wave rectifier is what we're going to be using by and large for the most part. Okay? Now, a rectifier is made up of a series of diodes. Okay? Now, on a full wave rectifier versus a half wave, we are using 4 diodes, okay? And this is what a diode will look like, okay? And I've got one more picture here. And basically a diode is a device that will allow current to flow in one direction only. It's a lot like a check valve for those of you who are familiar with hydraulics or maybe even fuel lines in your car. A check valve will allow fluid to flow in one direction, but if it tries to flow backwards, it will not. There will be a ball in there and a seat to block it off. Well, this is sort of the electrical version of a check valve. It will allow current to flow in one direction, but when an AC voltage, when you got an AC voltage on the positive side, it will allow it to flow, and when it goes to the negative side and tries to come back, because remember we're switching directions 60 times a second, when it tries to come back, it blocks it off. okay? For right now, I just want you to know that a diode is a solid state device that allows current to flow in one direction only, okay? So, the parts that make up a diode are the cathode and the anode, and this is the symbol for a diode right here. And you'll notice that it's got this little block right here. That's sort of like the gate, that's sort of the check valve, okay? We will allow voltage to go through the diode, and when it reaches its peak and reverses direction, again 60 times a second here in the United States, it tries to reverse, it gets blocked right here, okay? So we flow from anode to cathode, okay? Now, in the textbook, you might see where it says you're flowing from cathode to anode. That depends on whether we're looking at electron theory or conventional theory of electron flow. We're going to be using conventional for this lecture, so we're going to be flowing from anode to cathode, okay, from the big side of the triangle this way, but we can't come back through to the little side and try to go this way, okay, that's where it's going to be blocked. But my point here I want you to know is you got a cathode and an anode which make up the parts of the diode, okay? So you can also have a forward and reverse bias diode, but it's really what it is that's the way you've got it configured in your circuit, whether it will allow it to go this way or that way. That's basically the same diode, it's just how you've got it configured in the circuit. Okay, so I'm going to back up a little bit here, and we call this a full wave bridge rectifier. Okay, and we've kind of already talked about this part, but I'm going to go over it again with you here, and I've got a little file that will animate this for us in just a minute. But again, we've got our AC power, okay, and we are creating a sine wave, okay, it peaks to the positive, goes to our zero plane, then peaks to the negative, and then goes back to our zero plane. And remember, this is our peak. This is our peak voltage right here. These 2 points right here, it's where our voltage is peaking. It's peaking on the positive side here and the negative side there. This is the zero plane. Okay, and again, we're AC voltage going in to the primary coil of our transformer. All right, and then we're going to come out of the secondary coil. Remember this. We used 120 volts earlier, so we'll say this is 120 volts going into our primary of our transformer. Okay, we're 120 volt source going into the primary coil of our transformer, stepping it down to say 24 volts AC. Remember, all we've done is stepped it down. We have not changed it from AC to DC yet. Okay, so here we are, and we are going to feed our rectifier. This is our rectifier right here. Okay, with our load. Okay, and so we're going to feed our AC voltage into our rectifier. Okay, now here you see the 4 diodes. Okay, and they are positioned in here or soldered into the rectifier in a certain way, because we're going to allow a 1/2 of our cycle to flow through here. Okay, and then when it reverses and the negative cycle comes through, it's going to want to try to go back this way, and it won't allow it. My animation is really going to bring this to light. But what we've got here is we've got our AC voltage coming through here, going through our diodes, okay? And then we come through here and we get our DC voltage at these 2 points right here. This is where our DC positive and our DC negative, okay? So, and you'll see here, these are our D1 and D2 are our forward bias. That means they're closed. And the D3 and D4 means that they are open and will not allow voltage to go through there. Okay, let me show you this graphic here. Okay, to help kind of bring it up. All right, so first of all, we are building and collapsing. Okay, this is the first half cycle of our sine wave. Remember, there's 60 of these in 1 second. We're going to break it down real slow. This is our first half cycle of AC voltage. Okay, we're putting in that transformer, and we are getting a half cycle of voltage coming out here. Now, you'll notice that the voltage, this little ball is sort of representative of the voltage of this cycle right here. Okay, it's going through the anode through the cathode. Okay, and it won't go this way because remember, this is the check valve that's blocking it off right here. So we're forcing it through here. Okay, and then through here, and notice that it's going to go through this diode as well, okay? And that's going to give us our, and follow its path on back, but that's going to give us our DC voltage right here, okay? Now that is for the first half cycle, okay? Now, the second half cycle, it's going to go into the negative side there, and now we reverse directions. We were going this direction, now we reverse directions, and now we're going this way. Now watch what the little ball does here is in terms of the direction it needs to go. Okay, it's coming out of the transformer and going into the rectifier, and notice it's going through this way now. It's being blocked by these D1 and D2. It was being allowed to go through D1 and D2 the first half cycle. Okay, all right. Now the second negative half cycle, it's not being allowed to go through these, and it's now going to come through D4 and D3, okay? So what we wind up with are two half cycles right here of positive voltage, all right? And this is DC. Because it doesn't drop down below this the zero plane, we're not alternating between positive and negative. We are staying on the positive side. So now we have created somewhat of a simulated DC signal. We're not alternating below the line. We're staying above it. So it's somewhat it's a DC signal. But notice that there is a ripple. Okay, while it's DC, we can't have this. This is not good. We're not good. We're not there yet. But this is how we get a DC signal out of AC. We route it through the diodes. And the diodes are configured in such a way that it will allow the first half cycle positive ones to go through and create the first half cycle of DC, and then the second half it will be allowed to go the other way and creates another half cycle of DC. Okay, so we've got these two humps right here, and they are while they are DC, we can't have that kind of variation in our voltage like that. Okay, we've got to have a smoother ripple. But anyway. This is the symbol. This is the the rectifier itself, and we take the alternating current, and we wind up with a DC or more of a direct positive current only, and nothing on the negative side. Okay, so now there's a problem. Like I said, we can't have DC ripple like that going on in our circuits, particularly sensitive electronic circuits, because it's going to wreak havoc on those things. We need a solid, nice, solid, steady a signal of DC. So what we'll do, what a power supply will have inside of it is a capacitor. Okay. Now a capacitor, if you try to remember back from your AC/DC lessons, a capacitor is sort of like a storage bank, a storage unit. Okay. It will be charged up with DC voltage, and it will hold a DC voltage until it's needed. And whenever the voltage drops and it needs to give it sort of like a booster shot, it will release voltage based on how much is needed, okay? And it will help smooth out the ripple, okay? In other words, it takes up the slack. That's a good way to look at it there. It takes up the slack of when these dips in our DC ripple start to take an effect, okay? So we've already talked about how we're taking the AC, going through the rectifier, and we're coming out with our load, and our DC our load right here is experiencing this up and down. Still all positive voltage like a DC signal, but it's got a lot of ripple and it's not clean. So we've got to clean it up with this capacitor. So if you can see right here, what happens is as our voltage, I'll use this sine wave here, as our voltage is starting to peak, start to get to its highest point, we are also creating a DC voltage that's going up as well. Right here, it's going up as well. And when we do that, we are charging this capacitor. In other words, we're topping it off, so to speak. Okay, so we've got this capacitor completely charged at this point right here. Well, as we start to come down with our AC sine wave, we also come down with our we also start coming down with our DC signal a little bit. As we start to drop off, the capacitor senses that and steps in and gives it a quick hit of DC power to kind of get it from this hump to the next hump. Now remember, this is happening at 60 cycles a second, okay? Very, very quickly, okay? So this capacitor does not have like 4 or 5 seconds worth of charge or discharge time on it, okay? It's happening very quickly, and what we wind up with is we kind of start giving it a shot in the arm right here, and it holds it over until we can get back up into this next peak there on our AC signal, which results in a peak in the DC signal. It'll hold it over, And then remember, as we're coming up in voltage, okay, we're coming up in our signal here, we're recharging that capacitor. Starts dropping off, boom, hits it again, holds us over here until we can get it recharged, and then we wind up with a relatively smooth DC signal, okay? So now we've gone from this, okay, because you see there's no capacitor in our model of this rectifier, bridge rectifier. So with this, we're going to have a lot of humps and a lot of ripple in our power signal, but we go in there and we add that smoothing capacitor, okay? And then that basically smooths our ripple, and we get a much more constant flow. Now I'll tell you right now, nothing is as pure as the DC signal, that voltage that comes out of a battery, for example, okay? But this is very close, okay? So it gets really close, really good clean power, enough to where we can run our electronics. And again, if we didn't have this, okay, and we had this load, let's suppose this load here was a light bulb. Okay, we could run off a DC voltage. You can run a light bulb off of AC or DC. All right, but if we didn't have that smoothing capacitor, we had that light bulb right here. Our light bulb would be flashing. Okay, it would be pulsing. Okay, it would never experience the negative half of the sine wave like with AC, but with this DC, it would be peaking and dropping off, peaking and dropping off, pulsing and flashing. With this smoothing capacitor, we got a lot more even ripple, and you're probably not going to see any variation in the intensity of the light being put out through our load, okay? So this is the whole gamut with a bridge rectifier. And again, I'm going to go back to this as well. Power supplies that are used. For example, let me stop here for a second. You plug in your laptop or you plug in your phone, okay? Let's take a phone, for example. A lot of you, let's say with iPhones, they have the charging, the head that you plug into the wall, okay? And then you take a USB connection and it goes to your phone. Well, that thing going into the wall is nothing more than a power supply. It's taking the 120 volts and stepping down. How do I know this? Because you're not going to put 120 volts in an iPhone, okay? You have to step that voltage down, okay? And the iPhone does not, it has a battery in it. So we've got to rectify that AC voltage that we just stepped down from 120 volts. We got to rectify that into DC, and it's all done in that little charging head. If you've got a laptop and you plug your cable in, got the little black box there that's somewhere between the wall outlet and where you plug it into your laptop, that too is a power supply. It's simply no more than a small transformer. Usually they are electronic on transformers like that, and not the bigger industrial control transformers that we see. But the principle is still the same. You step that voltage down, you rectify it, and get you a nice smooth ripple, and you rectify it to DC. Some phones are like 9 volts, sometimes they're like 5, 7 volts, something like that. But anyway, that power supply gives the correct voltage going into whatever device it is that you're using, okay, or trying to charge. But anyway, that is the bridge rectifier and how we convert AC to DC. That's how it's done, okay? Now, a couple more things before we wrap this up. We'll talk a little bit about troubleshooting. Unless you are going to be an electronics technician, there's not a lot of troubleshooting involved in a power supply, okay? You put power, you check your power basically going in, and if you got power going into your power supply and you've got nothing coming out, nothing coming out with your meter, okay? And again, simply check with your multimeter. You're using, like for example, if it's 120 volts going into your power supply, check, make sure you're getting 120 volts from your power supply that's feeding the transformer. All right, and then check to see if you've got DC voltage. Switch your meter over to DC, whatever it's supposed to be. If it's supposed to be 24 volts, put it something higher than 24 volts, obviously, and measure to see that you're getting DC voltage out. Okay, that in a nutshell is the easiest, and probably about as deep as you'll go when it comes to a power supply. I'm going to use this as an example again. Okay, right here, I'm going to try to zero in on here this with a little bit. This is your power supply, and you'll see L and an N, line voltage and neutral, and there's also a spot for a ground. This is where you put your 120 volts, okay? And down here below, you'll see a positive and a negative, okay, and there's a ground as well. So it goes in 120 volts, and it steps it down to 24 volts. And here's the positive side and the negative side. So whatever it is I want to hook to it, for example, a light bulb, okay, I can hook it to the positive and negative. But basically, if I were to troubleshoot this power supply, honestly, I am not going to take the back off it, get into all the filters and all of the capacitors and things like that. I'm just not going to do it because it's not worth the time. I can throw this away and buy another one a lot cheaper than I can pay somebody to fix this. But I'm going to check my meter right here, put my meter here and check it, make sure I got input voltage, and then I'm going to switch my meter over to DC and make sure I got that I've got DC voltage coming out. Really, that's about all you do as far as power supplies. Now, if there is an opportunity for you to be able to get into that rectifier and take a look at it, okay, you can check. There are a few basic things you can check, and they're really quite simple. You can check with an ohm meter, okay. Put it in the ohms, okay, and your positive will go to the anode, and your negative will go to the cathode, okay. And you should get really low resistance. In other words, it should pass through very easily, okay. Because remember, we're passing through in one direction only, okay. Now, what we can do here too is we can flip that diode over, and now our anode is going to be touched with the negative, the black lead, and our cathode is going to be touched with the positive lead, and we should not get any type of continuity or any type of reading through here. We're getting an infinite, meaning basically there's no flow between this lead and this lead, because we don't want that flow to flow in the reverse direction, okay? So our anode being our positive and flow into our cathode, but we don't want the anode to flow from the negative side to the positive side. So you take your multimeter and just stick it on a diode, and if it flows one way, you switch it over and it does not flow the other way, the diode's good, okay? If you get infinite on both of them, or if you get readings on both of them, then you've got a problem with your diode. But other than that, that's really about the only way you can test a power supply. Okay, if it's got power coming in, great. If it doesn't have anything coming out, it's your power supply. And 9 times, I personally have never taken a power supply apart and pulled a diode out and replaced it. In situations, particularly when time is money out on the manufacturing floor, you've got to get the machine up and going, and you're not going to be taking that down unless there's a very special, specific reason. You're not going to be taking a power supply apart and getting down into the component level repair. You just chuck it and get you a new power supply, okay? But anyway, that is DC power. That's how we convert AC power to DC power. A little bit of how it's done, and also troubleshooting as well. But I hope you've gotten everything you need to out of this lesson. I hope you've been taking notes as well. If you've got any questions, be sure, first of all, be sure to take notes in your reading as well with this lecture. But if you got any questions, or you want to talk some more about these, find me in the lab. Be happy to show you. I got a couple of examples. We can take some power supplies apart and take a look at it if you want to. But anyway, that's what we got on DC power. I guess I will see you in the lab, if not before. Thanks for watching.